Because of Hurricane Irma and us having to redo this class and reschedule it, we are rescheduling vibe recording for next Monday. And as a take-home assignment, you're going to do a topography assignment. So this was scheduled for later on in the semester, but so that we don't get too far behind and don't have to do a Saturday, that we can come and organize and do this take-home assignment and watch this video. So first off, what we're gonna do is you got a couple of different assignments. So for our Merle's Inlet paper, what we're going to want is that not this Friday, but the next, we're going to have a due date for a rough draft of our introduction and our methods. So you'll find this cue sheet or the paper that tells you what the actual paper is on Moodle. So things we'll be looking at is we'll be writing an introduction, and that is broken down into 4 different parts where you're going to introduce the topic and a why, so the motives for the study. So this is, why is this study important? And why are barrier islands important? Why is sea level change important to understand? And then what we're going to do, you'll provide some background concepts. So what is a barrier island? How do the barrier islands form? Hint, that is in the Davis paper. He identifies 3 different models of barrier island formation. So you'll want to talk about those. The coastal morphology of South Carolina. So talk about the beach and how it looks and how it changes seasonally. We're on a passive margin, so explain what that means. That we have wave, the different barriers we see in this area, and then how the stratigraphy of a barrier island system can be used to study sea level change. So this would be the different areas of a beach. So in this point, we've already described the model or the ideal model of a barrier island, but then let's talk about how we can use the changing of stratigraphic layers to identify the history of the barrier island in relation to sea level change. Then you'll have a section that is based on the current literature review. You'll essentially write a summary for 2 different papers. We've already done the Davis paper, so you can use that. And we'll look up a second paper of your choosing that basically is something that applies to what we're studying. So I would definitely use something like Google Scholar. So this guy right here. If you look at that and basically Google barrier islands or South Carolina morphology or North Carolina morphology or something that is similar to what we are doing, it should pop up with a paper, a peer-reviewed article from that would be similar to us. Don't use Wikipedia, that doesn't count. We're looking for peer-reviewed scholarly journal articles. So geology, marine geology, Journal of Coastal Research, stuff like that. You can use the library. You can come talk to me if you have questions about that. But use a good resource. And then also, you'll provide your hypothesis and what you're trying to argue in your paper and goals. That's often a good part of that. And then we'll talk about our methods. So on this upcoming Monday, you'll come out into the field and actually collect some vibrocores. And so please, we'll want to pay attention to what's going on to write a section for that. So this is often a very brief section of the paper. What you're doing is you're describing in generalities what we've done in the field. So if there are specific measurements or specific things needed to know, then you'll describe those. Other than that, so we'll talk about how the cores go in and how they're removed. But this is not a narrative narrative of what you've done. It is a broad, general description of the step-by-steps of what we've done. So you don't want to go through and say this person did this. Instead, say, this cores were collected this way. And so we don't want to have any first or third persons in it. So this is written in passive voice and typically in past tense. So make sure we're writing that properly. And so we're going to have a rough draft of this by not this upcoming Friday, but the following Friday. All right, and there'll be a whole assignment, turn it in thing on Moodle for that. So now for our assignment that will cover us missing our Monday lab. And what we're going to do is we are taking this topography assignment we were supposed to do later in the semester, but doing it now because it can be used as a take-home assignment. Again, stop by my office or download the work packet off of Moodle and do that work packet and turn it back in by next Monday. So let's go over a little bit of what topography is and how we can use that to understand or represent data. So topographic maps simply are 2D representations of our three-dimensional world. And the way we do that is we have our area, and then we're representing elevation changes using contours. And all a contour line is a line of equal elevation. And so once we have these contour maps, they're known as, we'll make those contours, they're known as contour maps, and they're representing the topography or elevation change. All right, so here in one we've got we can see several different contour lines. So we've got some bold lines and some not bold lines, so they are occurring at different intervals. But we can see where we have a peak and then coming down with a lake and then coming back up. And so we can look at these contours shaped, and you can notice the certain numbers. Those are representing elevation. Sometimes on the really bold lines, they will give you the elevation that line represents, and you can follow that. So we've got a 1500 line right here, a 1050 over here, and so we can then figure out what those elevations are and their direction. So as we move from this contour up to this contour, we're increasing in elevation. And so we know we're moving up a hill in that direction. So again, we're representing a 3D model. So in the real world, we can have something like this island with a series of peaks, and then essentially just in this world drawing and saying, okay, well, where is sea level? Now our next contour will be in 500 increments. So this isn't all theoretical, so it could be meters or it could be feet. And so we have that there, and 1,000, 1,500, and so on. And so then those would just correlate to our contour maps. Again, we would be looking at the extent of a bird's eye view of this island so then we can see the elevation of that. And so we're creating a bird's eye view with contours representing elevation. All right, so while we're looking at these, we've got so for us to read them, we have our different contour lines. On a line, any time we go through this line, or that is a equal elevation. So anywhere, as long as you're on this line, that elevation would be 500. As you move to that next line, it's going to be a different elevation. But anywhere along that line, it is the same elevation. So we can show elevation and the shape by looking at these lines. And we can see our relief, which is the difference between the high and low elevations. So in this, if we add contour intervals, which is the difference between lines, there's typically two different ways of going about this. We have, most maps will always have a really bold line, and those will be one contour interval, and then we'll have really thinner lines, and that's going to be a finer interval. So our bigger ones in these are in 100 feet intervals, and then every one in between would be 20-foot intervals. And so we can use this to look at the gradient of slope, or the steepness of it, and also our shape. So we can see over here where these lines are closer together. That means there'll be more of a slope or higher gradient and steeper in this zone than something over here. All right. So typically it's every fifth line that is darker, and therefore that elevation is printed on the map. It would get really busy if every contour had an elevation on it. And so in order to keep our clean and easy to read, there's not always a elevation written on them. And that's where we really like or want those darker index contours or index lines to be represented. So we've got a couple of different rules for contouring. First, contours lines can never cross, because each contour line is equal to a specific elevation. So you can't have two lines crossing, because you can't have two different elevations at a single point. So they can never cross. Contours form closed loops, even if they're not shown on a map. So we can identify something like a hill because we start seeing an increase in numbers in elevation as we go, as given on this map. And so we know this is a hill. If we saw a decreasing in numbers as we went towards the center, then that would be a valley. Now, sometimes our map does not cover that system or entirely, and you may need one or two maps put together, or even several maps put together, higher land feature that would close those contours, but they are closed contours. I talked a little bit about your spacing. So the closer the spacing of the contours are, the steeper the gradient is. So over here we have a very low gradient because these are pretty far apart, so low gradient. And then over here these get much closer together, and therefore we would have a steeper zone. And so we can start to identify this and quickly be able to understand what the system looks like when it is just by using these contour lines. So sometimes we have to make contour maps, and this will be something you'll be asked to do. And so being able to understand how to do this, we'll be doing it through interpolation. So what this is we're drawing our lines basically in between the points. And so we are trying to figure out the best placement for our contour lines. So first thing we'll need to do is we'll have our different elevation points. So this could be if you're out mapping or collecting data and maps already made up, you may make them. So if you're out looking at ghost crab burrow elevations and want to then try to compare that to other major land features, so the dunes or where mean low tide level is or mean high tide level is, then that's something that you could use and create a topographic map with. So if you go and collect those elevation points and then describe a contour interval, you can start to circle if there is a if there's something that the organisms choose habitat or their burrows or nesting sites or whatever you're looking at. So these can be very, very important and also useful when looking for habitats and organisms. When we're interpolating, we're identifying our contours at 10-foot intervals. And so what we're wanting to do is basically play connect the dots. So, but we have to include or exclude numbers that don't work for those intervals. So if we have 100 and we want to make a 100-foot interval, we can't just draw a straight line right here because there's 101. Because what you're saying is anything inside of that 100-foot contour is above 100 feet in elevation, and everything outside of it is lower. So what we would need to do is draw it around. Go through and say, does this line have more or less? So what we can do is basically say we have 100. In yellow would be something that is included, so we can have over here 98 is lower than 100, but 101. Have to go through and say this is where it's going. Now 110, we can't just draw, but and somewhere in between here we'd have 110, because between 100 and 112 it'd go through somewhere here, probably closer to the 112 than the 100. Here's 112 to 101. Where would that line intersect here to be 110? And so on. So, a couple of tips. We're doing triangulated irregular networks, which is we're looking at the highest point, drawing straight lines to its nearest neighbors, and then start making decisions as to whether these are neighbors or if they are going to be excluded. So these are really rarely straight lines, and our contours can't cross each other, so keep that in mind. So we've started looking at these. 110, we have 100 and 112, and so 110 would cross somewhere near here. 100, 101, 112, and so we can kind of start looking at this. Same thing, we have 125, 125, and 112. And then 112 to 130. So we need a 120 contour. So that would cross closer to the 125 than the 112. Same thing over here, but somewhere in the middle of 112 and 130. So we can draw that contour line in. So when we're making these, we're trying to connect the dots. Sometimes don't exist. So we got to make them. All right, let's continue on. So again, when we're doing our triangular marks, so we're trying to figure out where on all of our triangles or locations that our contour interval would be, and then basically connect those ticks to create our contour. So often what we do, or what to set up, is we'll find our minimum and maximum elevation. Contour intervals, so we want to pick contour intervals that work for the map. So in the past map we just used, it went from 98 to 130. So we could have gone 10, or we did 10 meter or 10 foot contours. We could have done 5 foot contours. That could have worked. We could have done 2 foot contours. We like these even number deviations of 10, because then, you know, if you did 3s, that would be weird. 4s would get odd. So typically 1, 2, 5, and 10 work pretty well. But if we did every 1 meter or every 1 foot, we'd have so many contour lines that you almost wouldn't get to see anything. So just 1. We are able to see geomorphic features using these contours. We have what we call the rule of V's, and this helps us identify watershed boundaries. So we are pointing uphill, because as we get erosion and weathering, that's going to cut into the elevation features, making these drainage patterns. So a really quick identifier is when you see these V-shaped patterns, or at least drainages down to eventually into a river system. We also can see valleys. And so in something like this, if we were to contour, have peaks and ridges. So eventually, just like a rule of V, we have larger mountains over here and lower systems over here, so that we have V's pointing into this valley system. And we'd get to see ridges, gullies, and valleys in this, and be able to map them. All right, so that is the end of this. We'll talk on Monday.